Alright, everyone. We talked about PDE previously. We talked about how to solve it. Use implicit scheme, explicit scheme, Crank-Nicholson. Okay, and I show you how good is the answer when I use Crank-Nicholson. Oh. Okay, that's P. So, do you know how to do this by now?
We should.
You should, yeah. 1D heat equation. Just 1D heat equation. You should be able to do this, right? So we start. Do you know how to do non-dimensional lines? From dimensional form, this is a dimensional form, right? We can move from dimensional form to dimensionless form. Do you know how to do this? Yes or no? Oh, you should. You should, right? And I show you how to solve it. We talk about CFL condition, right? We talk about forward scheme, forward Euler, forward in time, central in space. The solution look like this. We talk about backward in time, right? That you have tri-diagonal equation and solve it. Use Thomas algorithm. So every point simultaneously, and then you get this. And then we talk about Crank-Nicholson. Crank-Nicholson, the right hand side, is just this term and that term. So when you do a little bit of math, you just get this is the same as backward scheme, and this is the same as forward scheme. So these two matrices you just multiply to each other so that you get one vertical matrix, right? It's known, it's defined at n. You recall this? So we already talked about Crank-Nicholson, and we talked about what is the oscillation in Crank-Nicholson. So when I satisfy CFL condition, it looks nice. When I not satisfy CFL condition, it's still solvable, but it has some oscillation. And this time, we will talk about 2D heat propagation. Just heat diffusion, but instead of 1D, this is 1D, right? Laplace equation just become d squared u by dx squared. So this time it will be y, d squared t by dy squared. So when it becomes 2D, it just has one more term. So we will talk about that. But a little bit before that, we will talk for the case where material property is not constant. Did I turn it on?
Yes.
Okay. So I upload a new, I call it appendix. That's appendix. So in the appendix, I try to discretize the 1D heat problem, but this time non-uniform thermal conductivity. Previous lecture, I talked about how to do the approximation, but that approximation is not correct. I mean, this approximation is not really what you want to do, okay? And we talked about that if we use finite volume instead, the derivation will be more rigorous. But it doesn't mean that if you use just finite difference, you cannot do it. You can do it, but it's not as rigorous as finite volume. Okay. For the case where thermal conductivity or thermal diffusivity is not uniform. So the full form, the dimensional form, originally it looked like, what is my original form? This one, right?
Yeah. This is x squared.
Originally, it looked like that. This is 1D heat problem, transient heat transfer in one direction for constant alpha. So the right hand side become this Alpha stay inside if alpha is not constant. Alpha is, what's alpha? We use it as K over rho Cp, right? We can take alpha out only for the case where material property is constant. If alpha change with x, then we cannot take alpha out from partial derivative. So you will have this instead. d by dx of alpha multiplied by dt by dx. Good? So if we don't have constant alpha, we have this. How do we discretize this? So I use central scheme twice. I do discretization for outside d by dx first. Think about the inner term as just parentheses. Okay? So that parenthesis at I minus half, I multiply by minus 1 plus 1 multiplied by that parenthesis at I plus half divided by delta x. So it's like the slope is delta y by delta x, right? So slope is delta y by delta x. Isn't that from this kind of table? Central scheme minus 1 half minus half. So it's like minus 1 x minus 1 and x plus 1. So x plus 1 minus x minus 1 divided by 2, or the gap, or the slope is delta y over delta x, right? That is central scheme. You see, both terms has divided by 2 because the gap between x plus 1 and x minus 1 is 2. Okay. So what I have here is the parentheses at I minus 1 have negative sign. The parentheses at I plus half, at I minus half and I plus half divided by the gap. The gap will be delta x, right? Make sense? So let's take a look at I minus half. Alpha at I minus half, so is do you need picture to understand this? Maybe a little bit picture will help. So we have grid point like this. Okay, we have I minus half and I plus half. Oh, plus half minus half. And over here will be I minus 1. And over here will be I plus 1. The gap here is delta x, right? Same as the gap over here. This is delta x. That's the gap, the interval, right? So that's why I have the parentheses at plus I plus half minus the parentheses at I minus half divided by the gap, which is delta x. So alpha defined at I minus half is the average between alpha at minus 1. So alpha at this point is the average between that point and that point. Make sense? So that's why I have alpha at I minus 1 plus alpha at I divided by 2. So this would be alpha at I minus half. What about alpha at I plus half? Alpha at I plus half will be 0.5 multiplied by alpha at I plus alpha at I plus half plus 1. So this means for alpha at this point, I average alpha at this point and that point together. Good? What about dt by dx at I minus half? dt by dx is the slope at that point, right? That's the slope. That's dt by dx. So dt by dx, I say, hey, it's delta y over delta x. So dt by dx at that point is t at I minus t at I minus 1 divided by the gap, which is delta x, right? So that's why I have this. Same as dt by dx at I plus half. dt by dx at I plus half is dt by dx over here. So this is t at that point minus t at that point divided by the gap. And the gap is delta x. That's why I get this. Right? George, any question with this? When we do it this way, do we need alpha to be constant everywhere? Yes or no, Daniel?
No.
No. Correct. So alpha doesn't need to be constant. Okay? Because we didn't take alpha out from the derivative. We have alpha stay over there, and we say, okay, the whole parenthesis at I minus half plus the whole parenthesis at I plus half divided by the gap. And for this term, we do the average. Let's move on. I just copy the equation from this slide to the next slide. Okay. Now, how about we do more like arithmetic? Simplify it. So I have 0.5 over here. I have 0.5 over there. I take 0.5 out. I have delta x over there, delta x over there, delta x over there, delta x over there. I take everything out. So I get 0.5 divided by delta x squared multiplied by the rest. Okay? And the rest is I just write it down. That I just multiply term by term, but this time I write it according to ti minus 1, ti, and ti plus 1. So I copy the simplified form, and when you look at this, what if alpha is the same everywhere? What do I get? I get this. Alpha over delta x squared ti minus 1 minus 2ti plus ti plus 1. Same as we use the central scheme formula directly. If we use that directly, we get that, right? We get that. So if you assume that alpha everywhere is the same, you believe me that I do the math correctly, so we get that. So this means this equation is more powerful. It's better. You like it? It's better in the sense that alpha doesn't need to be constant everywhere you use this. Okay? Good. So this means the coefficient will be alpha minus 1, alpha I minus 1, and alpha I for ti minus 1. And for ti will be alpha I minus 1 plus 2 alpha I plus alpha I plus 1, everything multiplied by minus 1. So this is the coefficient. Okay? So basically we have coefficient, but each coefficient for ti minus 1 minus, and the middle one and that one is just not the same. Okay? And if you write it, you can still do for the backward scheme. You can still do this. Okay? However, this time your coefficient won't be minus r here. It won't be the same. Why? Sure. Why your coefficient is not minus r and minus r? Why it's not the same? Because alpha is changing. Look at this, the simplified form. This alpha and this alpha, they are not the same. Right? So that's why you don't have minus r and minus r. Okay? But you can still write tridiagonal inverse it, and get the result. So for the case where material property is not constant, you can do it. Right? What if you have non-uniform discretization? Can you do it? What if Near the edge, you kind of discretize more for some reason, and away from the edge, you discretize less. What if that happened? What do? We do the same thing, but instead of delta x, we have to be more precise. Non-uniform grid. Oh, by the way, for heat conduction, you don't really need the non-uniform grid. You use non-uniform grid when you have turbulent flow. You have the change of the velocity a lot near the edge, and near the center is like more uniform. Okay, so you do non-uniform grid case in turbulent flow case, not even laminar flow. Okay, but I just showed you here. What do we do for the non-uniform grid? If the grid is non-uniform, we start with same equation, but instead of divided by delta x, we don't say delta x anymore. We say, okay, instead of delta x, we say xi plus half. Xi plus half is this, xi plus half will be this line, right? Minus xi minus half, which is this line. Starting from somewhere we don't know, but the difference is the gap. That's the difference. Okay? We modified a little bit for non-uniform grid. What about alpha defined at I minus half? We do the same trick. We use the average. Is that correct? Is it correct, George? Yes? No?
It can be wrong.
It is wrong. Why do I write it like that? It's your job to do it better. You should not use 0.5. Why?
Because the mean.
If you have non-uniform grid, this line may be over here, right? So it won't be in the middle. It won't be in the middle. If it's not in the middle, you cannot use 0.5, right? So you have to do linear interpolation if you assume that alpha change linearly. Okay? So that 0.5 there is written over there as a shorthand by assuming that we understand it's not right. But I don't want to write it too long. You don't actually use 0.5, you have to use some coefficient over here, some coefficient over there. Linear interpolation. Make sense? You should do linear interpolation over here too. Okay. But delta on the bottom, so dt by dx at I minus half will be I plus half minus I minus half, I plus half minus I minus half. Okay. I define delta xi equal to xi minus xi minus 1. That is delta xi. Then I can have, instead of writing it this way, I can say, hey, this time this is correct, okay? 0.5 delta xi plus delta xi plus 1. Why should it be 0.5? So I say, this gap is this gap plus this gap divided by 0.5. Or I say, hey, even though interval is not constant, but I just add half of the gap together. So this is a half of the east side, this is a half of the west side, right? I just add them together, so it's equal to this gap. Okay? So I have that. Alright? So delta xi previously is, I used delta xi and delta xi plus 1. Okay? So this is non-uniform gap. You do some more math, then you get this equation. This equation is not perfect, because if it is perfect, you should not have this. You should have some linear interpolation between these 2 points, but it may be too lengthy. You know how to do it perfect? Yes, of course. You have to do linear interpolation. You don't do 0.5 multiplied by alpha minus 1 plus alpha plus 1. You do weighted average instead of equal weight. Because your point is not in the middle, right? So what you will get is something else, not that, but it will be close to that. My point is, it can be done, maybe by you. In the project, you don't need to use non-uniform grid, okay? Just use uniform grid, it's difficult enough already. In the project, okay, where's the project? Let's take a look at project. Each of you have your own case. For example, the first one is for George, second one is for Nan, third one is Je, fourth. They are not the same. They're very similar, but they are not the same. So you cannot really copy each other. Okay? And take code from one person to use is not allowed. You get F. But to not have some temptation of doing that and make the problem to be different. It's not the same. If you ever copy it, even though I don't know, it doesn't work. That's my point. And if you know enough to modify your friend code to make it work for your case, you don't need to do that. Because if you know enough to do that, you do it from the beginning, it may be easier. Yeah. Okay?
On your code.
So, or you can modify it from my code.
Yeah.
So, cheating is discouraged. Not only you get F and I report you to the student conduct office, it's not the fast way to do. Okay? It's not a fast way to do. You see, in this case, you don't have the square shape, right? You have the shape that is like, some part is empty, some part has like material over here, some part you don't have anything. How do you do that? Any suggestion? I help you, I say, any battery that is not red or blue is no heat loss battery. No heat transfer, no heat loss. I mean, what is no heat loss battery? Mathematically, how do you write it? Adiabatic battery condition. What is adiabatic battery condition? Is it Newman or Dirichlet? Newman?
Newman, I guess.
Newman, you guess. That's correct guess. So dt by dx equal to 0. No heat loss, right? No heat transfer, no heat flux across the battery. So I say every battery is perfectly insulated, no heat transfer. Okay? And the red one is constant temperature battery condition. So for example, the red one is 100 C all the time, every time. Teal color is 0 C all the time. Okay. Initially, a little bit dark blue, this means it's 50 Fahrenheit initially. So initially it is 50 Fahrenheit. Yeah, 50, no, not 50 Fahrenheit, 50 Celsius. Everywhere that you have dark blue is 50 Celsius. Okay. And every battery is no heat loss. Except the place where it's red, it's constant temperature. Blue is constant temperature. Blue is 0, red is 100. So if you want to do something that is difficult, to do, you can, okay, you see the mesh. This is where you have 4 by 4 point, 16 point. You can discretize it this way. You don't use the corner point. Okay. So if you want to do it in a difficult way, the problem can be done in various ways. Okay. It's not single way of doing it. You have this kind of shape, right? So if you have the mesh on here, over here. Just that, and you have this. It's going to be difficult. So if you do this, so why is difficult? You don't have any grid point over here. It is correct, but it's difficult. You are about to see why it's difficult. Oh, by the way, in the project, you must use backward scheme. If you ever use forward scheme, you get 0. But you can use forward scheme to check if your answer is correct or not. But you must use backward scheme. Otherwise, okay, backward scheme. Let's search for the word 0. Yeah, you will get 0 for this project. If you use forward finite difference scheme in time, you will get 0. You must use backward scheme. Okay? We will revisit this later. Let's talk about what is. I just have square shape. How difficult it is. So I use dimensionless form. I just drop the tilde sign so that I type less, but I still mean dimensionless, okay? This is still dimensionless. So basically your equation is the dimensionless temperature, the dimensionless time equal to Laplace of t into d. You will do this for your project, okay? Is it difficult? Yes. Why? You say, okay, d squared t by dx squared equal to this. Can you do this? If your alpha is constant everywhere, you can do this. My material is copper, so alpha we assume constant everywhere. You actually don't want to do this, and there's a good reason for that. We'll talk about it. So if we have constant material property, we discretize it. You have 1 minus 2, 1 divided by the x squared. That's a second derivative with respect to x, right? We do the same thing for y. We get that. We substitute these two into our governing equation. And for the time, we have, or we rearrange it, and you will see that for backward scheme, everything defined at n plus 1 except Tij defined at n. So only this thing defined at n. The right hand side, like this thing, is defined at n plus 1. So that will be backward scheme in time. You still remember? For the 1D heat? For 1D heat, the left hand side, so is this forward or backward scheme charge? Backward in time or forward in time?
Forward.
Yes. If you have backward in time, this should be n plus 1. The right hand side should be n plus 1, right? So we have this backward in time. I rearrange it, I get this equation. The first portion is the same. You just have r and minus 2t, and this defined at n plus 1. And the second one is just different in j. So we don't just have left side, we have right side too. And this defined at n plus 1. Okay. Rearrange it, we get this. You know, if it is forward in time, it's a lot easier than this. Why? We just need. So look at this one. You need information at Tij, Ti minus 1j, Ti plus 1j, Tij minus 1, Tij plus 1. So this means you need like 5 points in the future. Okay, j plus 1, ij, j minus 1, I minus 1j, I plus 1j. So this is 5 points in the future at n plus 1. And you have 1 point at the current moment at n. So, but all this in the future, you don't have any information, right? This means you have to make equation for every point and you solve it simultaneously. Okay? What if it is a forward scheme? If it is forward scheme, you get this at n and one point at n plus 1. So this will be forward scheme, right? So this means if you know the information of 5 points at the current step, you can calculate the temperature at the next step easily. Yeah, very easy. So in the math form, it will be something like weighted average between 5 points of the current step to get one temperature at the next point. That's a forward scheme. Okay, but not backward scheme. So this means for forward scheme, your temperature prediction is dependent upon the current temperature at the previous time and the adjacent cell directly linked. Okay, not this cell or the cell around it that is not directly linked. Okay, that's forward scheme. Forward scheme is actually good. But you have to move slow. Okay, you still have some kind of CFL condition. You have to move slow. But if you don't want to move slow, you can use backward scheme. It's not that bad. So when we use backward scheme, we have to be able to move from this form to matrix form. Okay. So I define, after do some math, I define Q equal to 1 plus 4R. And R is our previous definition. What is our R? Oh, okay. R is, I think alpha over something. Don't remember, but I write somewhere. We have the definition for our R. Never mind. You find it yourself, okay? We have definition. Oh here. Delta T tilde by delta x squared. That's R. Previously we have Q equal to 1 plus 2R, but this time we have Q equal to 1 plus 4R. This is the equation for the edge or not the edge? Not the edge, right? So it's for inner point. The point where this equation apply. The boundary, if you have constant temperature or what? Direct boundary condition, temperature is constant. If you have Newman, but this case I simplified for you, it's not constant flux coming in, it's like flux equals 0. So this means after you discretize the temperature inside, you need to discretize the boundary condition too. Okay, I wrote here that we need 5 points, up, down, left, right, center, at n plus 1, and 1 point at n for the equation for the point at I n plus 1. So we need 5 points in the future and current point to get 1 point in the future. So number of unknown is more than number of equation. Okay, boundary condition. dt by dx at x equal to 0 equal to 0. If you discretize it, you have t0j equal to t1j. So the first index is for x. Okay. Do you, Daniel, can you tell me how do I get this?
I was about to ask you a question.
Okay. dt by dx at x equal to 0. Let's take a look where x equal to 0. Oh. So at x equal to 0, let's say this point. dt by dx, how do you discretize it? At that point, let me call that t1 and then T2. Okay, this means dt by dx, I can say, hey, dt by dx is T2 minus T1 divided by delta x, right? And it's equal to 0. This means T2 equal to T1. Make sense? So that's how, so this means this temperature equal to that temperature for the left boundary. For the top boundary, this temperature equal to that temperature. One by one, element by element. For the right boundary, that temperature equal to that temperature because this comes from this. So I may use forward scheme for finite difference on the left boundary, and I use backward scheme for finite difference on the right boundary, but it doesn't matter. At the end of the day, what you get is temperature at the edge is the same as the temperature next to the edge. Okay. For the right side, x equal to 1, dimensionless x. Okay. At x equal to 1, this means at t capital N, j at any j is equal to t at n minus 1 at j. So the point that next to each other on the right edge, they are the same because dt by dx is equal to 0. Okay. For the top one, dt by dy, y equal to 0, I get this. So bottom one is this. No heat loss at any n. That's the boundary condition that I said. Initial condition, I say one point in the middle is hot initially. So I have one point in the middle hot. Every edge is insulated, perfectly insulated. What happened with time? Okay. So let's start with 4x4 mesh. We do not need and must not have equation for the corner. We don't care about the corner, right? This point linked to that. So temperature at that point equal to temperature at that point by boundary condition, correct? Temperature at that point equal to temperature at that point by boundary condition. Temperature at that point equal to temperature at that point. Temperature at that point equal to temperature at that point. So when they are linked at the edge, they are equal to each other. So this means we have how many equations? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 equations. What about that point? That point link point around them and the point itself. So that's one equation. And we have equation for that point that link the point around them. Right? And we have the equation for that point. So we have equation, number of equation and number of points. They are equal to each other. We can solve it in theory. Okay? Let's take a look. So I get this. Wow, what's this? What's this about? Let's take a look one by one. See, T01, I call it J and I. So this is T00, T01, I equal to 0, J equal to 1, I equal to 0, J equal to 2. Okay? So first equation I have, first row multiplied by column. So this means T01 minus T11 equal to 0. What is T01? Let's go back. T01 is that point. T11 equal to that point. Right? T01 minus T11 equal to 0. This means T01 and T11 equal to 0. So this is the way I put this kind of boundary equation in a matrix form. So the first line comes from boundary equation. Let me check. Question?